Hello everyone and welcome to Lecture today. Today we'll be talking about the second big integral theorem, which fully generalizes the fundamental theorem of calculus. The last lecture was about Stokes' theorem, or the Kelvin-Stokes theorem, which is one of the multidimensional extensions of Green's theorem. Today we'll be talking about the other multidimensional extension called the Divergence Theorem. So what we want to do right now is, just like before Stokes' theorem, we'll recall Green's theorem in the plane. Specifically, we're going to recall Green's theorem in the plane. But if you remember at the end of the Green's theorem lecture, I talked about two different forms for Green's theorem in the plane. We can express it in terms of the curl of a given vector field f, but we can also express Green's theorem in what's called the divergence form. And the idea here is that we have some curve C that bounds some domain D, and as long as all of the considerations for the vector field in the assumptions of Green theorem hold, we can definitively say that the closed line integral over C of some vector field G dotted with n hat, and this is the line integral over the arc length of the curve, or over the length of the curve, is going to be exactly equal to the double integral of the divergence of G. Inside the region D. This is the double integral over the region D of the divergence of the vector field G. And really, in a very natural way, what this is telling us from Green's theorem is that the accumulation of divergence of the vector field G inside the region D is exactly equal to the flux of the vector field G normal to the boundary. So the flux of G along or normal to the boundary curve C. This is exactly what this theorem is telling us. The divergence theorem offers us a direct extension of this, but for three-dimensional volumes and a closed two-dimensional surface surrounding those volumes. And really the heart here is to kind of think about what we're doing when we integrate a given function, take the double integral of a given function, because we'll see the direct extension to triple integrals as well. So if we kind of consider a very small patch, we kind of zoom in on that patch of the surface. Let's say we zoom in on a very small patch. We know that when we're integrating or taking the double integral of a domain, it's the right-hand side of Green's theorem, we're essentially cutting up that region into a whole bunch of very, very small rectangles and approximating the accumulation in each of these regions by taking the value of the function at a sample point inside the interval and multiplying that by the area. And this is exactly what the double integral is in terms of an exact limit. So let's zoom in here. On just a very small patch and take a look at what's going on. And I guess I'll probably draw this a little bit nicer. I'll take a small patch of nine rectangles. And so the idea here is that if we have our vector field G, which is defined at all points throughout our domain, we know that the divergence of G is in some sense giving us an idea of the amount the vector field is stretching or diverging from every given point. If it's negative, it means the point's a sink, and if it's positive, it means the point's a source. So in our Riemann sum approximation, we can kind of visualize this as every point we have some degree or some measure of divergence diverging away from each one of these points. And what this Green's theorem in the plane is essentially telling us is that in the limit for the Riemann sums of this double integral, just like, by the way, for the limit of Stokes' theorem, in the very, very almost exactly the same way as Stokes' theorem, right? In the limit, as these rectangles get smaller and smaller and smaller, the pointwise value of the divergence in neighboring cells is essentially equal and opposite. So, for instance, the amount of divergence outside of this cell or moving in this direction essentially cancels with the divergence moving outside of this cell, as long as the vector field G satisfies all of the smoothness restrictions that we talked about when we developed Green's theorem. And so the idea here is that this is saying that we get this propagation effect where so this accumulation is going to be directly equal to just, we have all these cancellations, this propagates outward to the boundary. And this is telling us that the total accumulation of the divergence inside this region D, the double integral of divergence, is exactly equal to the action of the vector field G normal to the boundary, the flux of the vector field normal to the boundary. So in a very real way, right, our extension is going to be based on this idea, and you can actually go through and prove this very, very nicely. So I'll go through and offer a relatively straightforward proof of the general Gauss's theorem, and I'll write that down in general on the next page. But the idea here is that we're going to be considering now extending this idea to general surfaces. So let's say we have some surface S. That contains a volume V. V is the volume, three-dimensional volume inside the surface now. This picture is now in 3D. We can directly go through and kind of view, again, the triple integrals over V as an approximation, just like, double integral is defined via a limit of the Riemann sum approximation. As such is the triple integral over region V, where if we zoom in on some small portion of this region, we're actually integrating over cubes. And as these cubes get smaller and smaller and smaller, we arrive at the double integral, or the triple integral. I'm just going to draw 4 of these cubes right here just to kind of illustrate the point that I'm talking about. Well, what the divergence theorem is going to be saying is that we're going to have the exact same effect. So that Gauss's divergence theorem is saying that if we compute the flux, or the accumulation of flux inside this three-dimensional region, that's giving, in some sense, in the accumulation of the flux flowing outside each one of these small boxes in the Riemann sum limit. And again, just like before, as these boxes get smaller and smaller and smaller, you get a cancellation effect on the boundaries in every given direction. Perhaps a visualization that'll better show this is to take a standard shape and just kind of fill it with cubes, which is exactly what the process is if you want to be analytical about what the definition of the triple integral is. So I'll open up a plot just kind of showing this idea for a couple different surfaces. And first we'll just consider the sphere with 10 cubes. Move it 1,000 cubes here. You see that the approximation to volume is relatively not nice because you have a lot of error. However, if you increase the number of cubes approximating the integral of a function on a sphere, this is 20 cubed, you end up getting a much nicer approximation. I've colored these cubes to indicate that you could have a scalar function of 3 variables. So the function could be changing throughout your region, and the triple integral of that function is just the accumulation of that function inside the region, like from a normal multivariable calculus course. But what we're seeing as we increase the number of cubes, slowly but surely, it takes a little bit longer to run with a lot more cubes. This is 30 cubes. We're seeing that our approximation to approximating the volume with these cubes is getting better and better and better. There's still some error, but as we increase the number of cubes, we're getting closer and closer and closer to the boundary. And not only that, but the value of the function inside cubes that are neighbors to one another or close to one another, it's getting closer and closer and closer to the same value. So this is, again, the basis of that, going to be the basis of that cancellation effect that we talked about before. Now, you can go through and show some of this stuff using just Riemann sums, but I like just showing the idea using Riemann sums and then going through and proving the theorem in general using what we know about triple integrals and surface integrals. So I'll show this for the sphere for 2 more. This is 40 cubed. You can see that we're getting very, very close. And the relative values of the function inside each one of these, on each one of these cubes, is getting closer and closer and closer, which is supporting the idea that I mentioned earlier that if this function is measuring the divergence of a vector field, if the divergence here is approximately equal to the divergence here, the divergence along the faces of each of the cubes is going to cancel out. And so the divergence, total accumulation of divergence inside this region should be exactly equal to the divergence on the boundary. And this is exactly the statement of Gauss's theorem. And this will be my last plot of the sphere here with 50 cubes. And as you might expect, it takes a little bit longer to run. But we still see exactly what we want, which is that as these cubes get more numerous, they become smaller and smaller and smaller, and the function becomes approximately equal in neighboring cubes, neighboring cells. This is really the basis of the divergence theorem. Now, it's important to note that we can also do this on more complicated shapes. For instance, the torus, or really any complicated shape that you can think of, can be thought of as if you're going to get the accumulation of a function inside the region, you can think of it as it's the limit of the sum of the volume of each one of these cubes multiplied by the sample point of the function inside the cube. And that gives you an approximation to the total accumulation, and that's where the triple integral of a function comes from. This is for 10 cubes. This is for 20 cubes, and you can see that it's definitely getting closer and closer. We'll just jump up to 40 cubes. And this is showing very clearly what I was talking about before, and which will continue to happen for smooth enough functions as long as the function is smooth enough. As the cubes get smaller and smaller, the function is approximately constant across the neighboring cells. It's a little bit more hard to see here, but you can definitely see it as you increase the number of cubes. So if we go to 60 cube, which might take a little bit to run, you can see that even in those regions where the function is changing sharply, as long as it's changing in a smooth enough manner, which this function is, I think I chose the function x squared minus y squared plus z squared. You see that even in where the function is changing sharply, you're getting, as the cubes get smaller and smaller, a nice transition from the positive values of the function to the negative values of the function. And this will continue to happen because the triple integral is defined as the limit as these cubes go to infinity, the number of cubes, which is saying that the size of the cubes goes to 0. So as long as your function is smooth enough, this is going to work out very nicely. And you get this cancellation effect that I talked about earlier. So this gets us to the main part of the lecture, where I'm going to state the theorem. I'll state the divergence theorem, and we'll go through then and prove it, and then use it in some applications. And this is the divergence theorem. It's due to a number of different scientists and mathematicians, namely Gauss, Green, and even the Russian mathematician Ostrogradsky. And this is telling us the following. So we're going to let volume V be a bounded solid region in three-dimensional space whose boundary we will call S. In certain sources it's denoted, so it's sometimes denoted a partial derivative sign next to the V for boundary of V. And S consists of finitely many piecewise smooth closed orientable surfaces. These are all the three important assumptions. We will also assume about the surface that the normal vectors are all oriented consistently. And typically we take this as to be away from V. But we need this to be true. And you can alter the theorem if you want the flux in, but the idea is that divergence theorem is for flux out of a surface. Because it's an orientable surface, we can always do this. And second, we'll let F be a continuously differentiable vector field. Or a C1 vector field on V. So if all these assumptions are true, then we have that the closed surface integral over the boundary S of the vector field F dot n hat ds, which is the flux normal to the boundary or out of the boundary, is going to be exactly equal to the triple integral over the region V of the divergence function of the vector field F, the divergence of the vector field F, dV. Like before with Stokes' theorem, I really can't overstate how important this theorem is, because this is a completely separate generalization from Stokes' theorem, the generalization of Green's theorem in the plane, to now volumes and surfaces in 3D. And it is a direct extension in the most real way possible of the fundamental theorem of calculus from single variable calculus. Because it's saying, in some sense, that this accumulation of some divergence inside some interval, or this, in some sense, a certain type of derivative of the function f, the accumulation of that quantity inside the space V is exactly equal to the function being differentiated, evaluated on the boundary. So it's a very, very, very nice and powerful theorem. And the number of applications of both this and Stokes' theorem are innumerable. But what we'll do right now is, directly jump into the proof of this. And our proof is going to be kind of based, just like for the proof of Stokes' theorem, it's going to be based on two parts. Our first proof is going to be to go through and do this. So this is step 1 right here, and I've already kind of drawn some pictures here to make sure that you got pictures. So you want to copy these pictures into your proof, into your notes. But for step 1 of our proof, we're going to assume that S is a simple surface along the x, y, and z axis. Right, and remember, we defined simple curve for simple region D. Right, so this region V is going to be surrounded by a simple surface where we can express the top of the surface, the bottom of the surface, the left of the surface, and the right of the surface, and then lastly the front of the surface and the back of the surface as functions. Right, so for instance, S up right here. The surface itself is the union of S up and S down, but S up is parameterized by Z is equal to some function ZU of X and Y for X and Y in the region R1. And then likewise, S down will be parameterized by Z is equal to Z down of XY for X and Y in the region R1. Right, this is one way of describing our surface, but we're going to assume it's simple in every single direction. So each direction along X, along Y, and along Z. So we could also parameterize the boundary as S right, where S right is giving us X is equal to a function XR of Y and Z. And likewise, S left so the left side of the surface S, the closed surface S, can be described as a function X is equal to XL of Y and Z. And this is for Y and Z in this region R2, which is the projection of R onto the ZY plane. So here Y and Z are in R2. And so just like we're assuming it's simple along the X and simple along Z, we're also going to assume it's simple along Y. So you have that, you can determine the front of the surface, which I've called this portion of the surface. So this is Y is equal to some function YF of X and Z. And S back of the surface S back is Y is equal to some function Y back of X comma Z. And both of these are for X comma Z in this projection region R3. which is just this surface, the volume projected along to the zx plane. So this is the setup, and the idea is that for step 1, we're assuming a simple surface, because what we'll see is that any reasonable surface can be expressed as a union of simple surfaces. And thus, if we can prove it for a simple surface, then by cleverly connecting the simple surfaces for a more general region, we can go through and do this, just like for Green's theorem, by the way. So let's just consider the following. Remember, the divergence of f Cartesian coordinates is the sum of dp dx plus dp dy plus dq dy plus dr dz. And so the double integral, or the triple integral of this divergence is the triple integral of this plus the triple integral of this plus the triple integral of this. So we're going to consider the triple integral of just the first part of this divergence. The triple integral over v of dp dx dv. And remember, we can evaluate this in any order that we want because it's a triple integral. So if we assume that S is a simple surface, and region V is a simple region, then we can evaluate this as the double integral over R1 of the integral from Z, or sorry, not R1. But we got the YZ plane here, so it's this one right here, this R2 right here, the double integral over Y2, or R2, from the lower surface, or the left surface, so XL of YZ, to the upper surface XR of YZ. This is the triple integral of dp dx. This is in the order dx, dy, dz. And what's really, really nice about this expression is that, we know how to exactly go through and take this integral. This is saying take the definite integral of dp dx with respect to x. So from the fundamental theorem of calculus, this is going to be p, the function p, evaluated at xr of yz, minus p evaluated at xl of yz. And the integration term that comes up when we do our partial integration of this function ends up canceling, actually, from the fundamental theorem of calculus. So this ends up becoming the same thing as the integral, the double integral over R2 of P evaluated at X R of YZ, comma Y, comma Z, minus P evaluated at XL of YZ, comma Y, comma Z. And at first, this may not look super helpful, but rest assured, it's going to be very, very helpful. So we also want to likewise note, if we go through and do this process, for the other partial derivatives, or for the other terms, we're free to choose our order of integration for each one of these triple integrals. So we do the same thing for dq dy, dr dz. What we're going to attain is that the triple integral over v of dq dy dv is going to be equal to the double integral over R3 of q evaluated for y on our front surface. So it's x comma y front of xy, or of xz comma z minus q of x comma y back of xz So this is what we're going to get when we do the triple integral of dq dy, and when we go through and do the triple integral of dr dz, we will also get the double integral over R1 of r of x, y, and then z upper minus r of x, y, z lower. And so this is going to be our first step here into showing this theorem. Remember, we're only just going through and trying to show Stokes' theorem, or the divergence theorem, for a simple domain B, a simple surface S. But the idea here is that now we want to see, right, how does this kind of connect with the surface integral term. And we're going to do this by evaluating the surface integral along of specific portions of the vector field. So recall the parameterizations, right? For both S upper and S down, so S up and S down, the parameterization is for points x, y in R1, and our parameterization is of the form R of x comma y is equal to x comma y comma h of x comma y for some function h. For S up, this function is the function zu, and for S down, the function is zd, the bottom of the surface. But no, both cases parameterizations take this form, which means the normal vector is going to be plus or minus ru cross, or rx cross ry which we've shown a number of different times. For the graph of a function, this is going to end up being negative hx, negative hy, and then positive 1. Because remember that this is just the cross product of 1, 0 hx with the 0, 1 hy. And so this is equal to right here. So the idea is that this is our normal vector is going to be plus or minus this, depending on the orientation. And the idea is that we can do a similar thing for both S front and S back. Or S front, S back, is a surface that's parameterized for x and z in R3. And so our parameterization is r of x comma z equal to x, and then some function h of x, or h of x comma z, which is like our function y front and y back from before, and then the z coordinate is the best parameterization in terms of Cartesian coordinates. And so when we do take the normal vector rx cross ry, or rx cross rz, we're going to end up getting the normal vector, and this will end up being a little bit different because of the structure of this parameterization. I'll get hx negative 1 hz. But remember, we have to choose these normals consistently, so like this is what we'll be doing when we go down and get to the very end. So it's important to remember that in any parameterization, ds in your integral, in your surface integral, is always going to be plus or minus ru cross rv du dv. When you do your surface integral, you plug into your surface integral. So the idea here is that the plus or minus here depends on the orientation to the surface, and so we have to just make sure that we do an outward normal choice for each one of these. But regardless, plus or minus this will always point outward to either SU or SD. Plus or minus this vector will always point outward or inward normal to SF and SB. And then lastly, we have SL and SR, which is parameterized for all points y comma z in R2. The most natural parameterization for both is in Cartesian coordinates, going to be some function h of yz, where this is going to be xl or xr depending on which of these surfaces we're talking about. And then it'll be y and z, which will then give us an rx, or rx cross, oh sorry, not x here, there should be h of r of yz here. So the normal vector to either of these surfaces you can get by doing ry cross rz. Which is going to be, when you do this cross product of ry cross rz, you end up getting the vectors 1 negative h y negative hz. So for our surface integrals now, we have a correct parameterization for our normal vectors, and we're actually now ready to go through and finish the proof. So we have just one more step in this part 1, step 1. And this is going to be, in some sense, a little bit of, not a trick, but a nice way of decomposing our vector field. So we're going to use the fact that our vector field F is just P, Q, R, or P I hat plus Q J hat plus R K hat. Pi hat is just P00 plus Qj hat is 0 Q0, and Rk hat is 0 0 R. And the reason that we're doing this is just like before, where we split up our volume integrals, the divergence, and we computed the three components of divergence in Cartesian coordinates, the three parts of divergence, not components. For the volume integrals, we're going to go through and do the same idea here for the surface integrals of the three parts of this vector field. Or if we use this decomposition, the surface integral of f dot dr is the same thing as the surface integral of the vector field pi hat, not dr, ds. ds over the surface S plus the surface integral of qj hat ds. We have a dot product here as well. And then lastly, plus the surface integral of r k hat. And we're going to consider each one of these integrals individually, because this is where the real magic is going to happen. Specifically, we'll start by just considering this integral right here. So you'll recall that this surface integral over S of r times k hat we can think of as the sum of the open surface integral over S upper with the surface integral over S lower. Assuming that the normal vectors in each case have to be oriented consistently to point outward. So let's focus on one of these, the surface integral of S upper and when we go through and apply our previous parameterization, this is the same thing as the double integral over R1 of 0, 0, because we're doing just the surface integral of r k hat. This is going to be then the third component r evaluated at this parameterization, which is r of x, y, and then the function z upper of x, y. And this is going to be dotted with the normal vector. In the normal vector, we found before to be negative the partial derivative of z upper with respect to x, negative the partial derivative of z lower, or z upper with respect to y, and then 1 was the third component of this cross product. Du dv, or dx dy. And something very nice happens here. This dot product completely doesn't depend at all on the first two components of these vectors. This was specifically of the normal vector, because 0 times this is 0 and 0 times this is 0. So this just becomes the double integral over the region R1 of the function r of x comma y comma z upper of x comma y dx dy. And likewise, when we consider the surface integral over S lower, so the lower surface, we get that this is going to be the double integral of the vector field R, evaluated not at z upper but at z lower. And we have to multiply this normal vector by -1. The point has to point outward to the surface, so in the negative direction. This becomes positive, positive, negative. And so this just becomes the double integral over the region R1 of the vector field R of x comma y comma z lower of x comma y times -1. And what's remarkable here is that when I add these two things together, I get the closed surface integral over S then is going to be the double integral over R1 of R of x comma y comma z upper of xy minus R of x comma y at z lower of x comma y dx dy, which is exactly the same thing. Oops, let me make this a little bit. The closed surface integral of this right here So this is really incredible, because what we've shown is that this surface integral of r k hat over the entire surface S is the same thing as the integral over region 1 of r on z upper minus r on z lower, which we showed from before is the same thing as the triple integral over the volume V of the partial derivative of r with respect to z. And likewise, we can go through and show the exact same result for qj hat and for pi hat, which connects this expression right here and this expression right here. So this essentially concludes the proof, because what we've shown is that the triple integral over the volume V of the divergence of f by the definition of how we've defined divergence is the same thing as the triple integral over V of partial p partial x plus the triple integral over V q dy and dr dz. But what we've shown is that this is the same thing as the surface integral over S of PI hat dot ds plus the surface integral of QJ hat over S plus the surface integral of RK hat. Which is just equal to the surface integral of the full vector field F over our closed surface S. So this concludes the proof for step 1. Step 2, you want to note that the previous proof is for simple S. However, if S is not simple, we can break it into simple pieces. And the flux across each, the intersection will cancel. So for instance, let's say S looks like this. We can introduce a cut, or this cut we'll call M, which is the surface that's bounding these two pieces. We'll call the top piece S1 and the bottom piece S2. And because S1 union M and S2 union M are both simple domains, our previous proof holds. So we have the surface integral over S1 union M of F dot ds is going to be the sum of the open integral over S1 plus the surface integral over M and likewise the surface integral over S2 union M of f dot ds is going to be the open surface integral over S2 of f dot ds minus the double integral, or the surface integral over m of f dot ds. And this negative just comes about because the outward normal to S1 is in this direction right here, but the outward normal to S2 on m is in this direction right here. So the outward normals on each of these surface integrals are opposite one another. And because it's the same surface, when we add these two things together, we end up getting that the sum of this plus this is the same thing as this sum plus this right here. Which gives us a cancellation because these two values are the same. These two integrals are the same, but they're opposite sign. So this is just equal to the total surface integral over S itself, or S1 union S2, and the divergence theorem applied to both S1 union M and S2 union M is giving that this is the divergence over this region, or the triple integral divergence over V1, and this is the same thing as the triple integral over S2 union M, or over V2 of the divergence of f. So the sum of these two things becomes the triple integral just of the divergence of f over the entire space V1 union V2, which is just V. So this is it. This gives us the proof of Gauss's theorem, which is we'll go over now a bunch of different applications of this to show how we can use this in practice.